Okay, so we're going to do this activity. So in the first question, it says create an unsimplified polynomial function that satisfies the following requirements. In format f of x equals x. It has to have at least two terms with x, no more than 4. After simplification, highest exponent in expression must be not greater than 3, and at least one exponent rule must be applied to function that will be simplified. There are some examples. Okay, so this is what we did. The function that I did was 2x to the power of 2 to the power of 3 over x4 plus 3 to over x to the power of minus 2 plus 7x plus 2. So to simplify the polynomial function, first you have to simplify these exponents. So you have to elevate 2 to the power of 3 and multiply the exponents of x. And on the other part of the function, you have to bring this x to the minus 2 onto top of the fraction with the exponent, with a positive exponent. Then to simplify, you just divide the exponents. So you have to subtract this exponent. So 6 minus 4 equals 2. So it's 8x6 over x4 is 8x2, like you see here. And then you just put like terms together. So 8x2 plus 3x2, it's 11x2 plus 7x plus 2. Okay. Then for the third point, you have to find the derivative function using the principal's formula. This is the principal's formula. It's a limit. So okay, you have to apply this to the function that we defined, this one. So you applied it. So the limit when h approximates to 0. So where you see an x, you have to put x plus h. It's f of x plus h. So you put 11x plus h squared plus 7x plus h plus 2, and then you subtract f of x, that is the original function. So it's minus 11x2 plus 7x plus 2. Then you solve the parentheses, or you do the FOIL, and then you distribute this minus sign, so all these terms become negative, and then you have to multiply this 11 for all the terms inside this parenthesis. So it would be 11x squared plus 22xh plus 11h squared. And then you put like terms together. You see that 11x squared cancels with this 11 squared here. The 7x cancels with this 7x. That 2 cancels with this 2. And then you are left over with this expression. What you do next is to take a common factor h from this expression on the top, and then you cancel it with the h on the bottom, and then you apply the limit. So what you do is put the 0 where there's an h. So if you put the 0 on the h, this becomes 0, and you are left over with 22x plus 7. And that's the derivative using the principal's formula. So as you can see from this, we can conclude that the derivative of a polynomial function to the power of 2, as we see we have a function to the power of 2, becomes a polynomial function to the power of 1, because you can see that the derivative is x to the power of 1, the polynomial function with x to the power of 1. And in general terms, the derivative of a polynomial function to the power of n is a polynomial function to the power of n minus 1. As you can see, if you call x to the power 2 n, and then the derivative is to the power of n minus 1. So it's 2 minus 1, 1. That's that explanation. Then you have to find out a derivative using the differentiation formulas and explain it. So for a polynomial function that is shown as this form, x to the power of n, the derivative is n times x to the power of n minus 1. And also you have that the derivative for a function that is constant is going to be 0 every time. So if we apply these formulas to the function that we had, you can see that if you apply that derivative to our first term, you have 2 that is the exponent multiplied 11 times x to the power of n minus 1, that is 2 minus 1. Then you have 7 times 1 times x to the power of 1 minus 1. And that is x to the power of 0. And if you see, then you have the constant, the 2, and the derivative is 0 always. So you can see that you are left over with what? With 2 times 11 is 22 times x to the power of 2 minus 1, that is x to the 1. And plus 7 times 1 times x to the power of 1 minus 1, that is x to the power of 0. And anything to the power of 0 is always 1. So it's going to be 7 times 1. And you see that we have the same answer, but we use different methods to achieve it. Okay, what's next? You have to explain what the answer from part B signifies. No. Okay, so now we're explaining. Okay, we're going to point 5. So point 5 is going to be to choose any point on your function, apply your derivative to this point, and explain what the answer from part B signifies. Okay. So let's take this example. We're going to use the point at x equals 1. And if we apply x to the function, x equals 1 to the function, we see that it gives us 20. So we have the point 120. And if we use the derivative, that we have this function, this is the derivative function, and we apply that point to the function, we see that the derivative at x equals 1 is equals to 29. And this means that the slope of the tangent line to the graph of f of x to the graph of this function, the slope of the line that is tangent to that graph is going to equal 29 at this point. At this exact point, the slope of that line is equal to that. Or in other words, we can say that the derivative of f of x at the point 120 equals 29. Okay. Next, we have what is the relationship between the slope formula and first principles formula. How is your directly related to your function, and what is the relationship between the general derivative and the derivative of at the exact points. Okay, so we have this graph, and in this graph we can see that we have a function f of x that we are going to call it position. We also define what is the average velocity of a particle. We can see it as a particle. It's always going to be the change in its positions over the time of the change in their time, and that is the average velocity. And we can see it from like this way, like the slope way, x2 minus x1 equal over t2 minus t1. And then, as we can see, if we call this f of x the position, and we're going to find the average velocity as the slope of a straight line, we need to take 2 points. We're going to call this point x and this point x plus h, and the distance between these points is going to be obviously h. And if we apply the formula, we're going to see that we're going to have the slope formula. We're going to have f of x plus h minus f of x over x plus h minus x. And if we cancel the x's, we are going to end up with this f of x plus h minus f of x over h is going to be the average velocity. And this is the slope of this straight line. But when we are talking about that derivative, we are talking about that line that is tangent to this graph, but this line is not tangent. If we want a tangent line, we need a line that is going to appear in this part. In that exact point, you have a line like this, and it touches only in one point. How do we get that? We need to bring this distance as closer to 0 as we can. And how do we do that? We need to apply the concept of limits, because if we apply the concept of limit, we are going to approximate this slope to this point, to a point where h equals 0. And then we're going to end up with this formula, that is the formula of the principal formula that we use to find the derivative. And what is the derivative in this case? It's going to be instantaneous velocity, because it's going to be the slope of the tangent line in exact points. It's going to be in an exact point because a tangent line touches a graph only in one point. So there's that explanation. Like I said, it's a derivative in an exact point. Okay. The next question says, how is that is your derivative related to your function? Okay. So the derivative tells us a very important information about the function, because if you know what's the value of the derivative, you know how the original function behaves. For example, if you know that the derivative is positive, you certainly know that the original function is increasing in that exact point. And on the other case, if the derivative is negative, it means that the function is decreasing at that certain point too. Okay, that's that. We can conclude that if you know what the derivative value is, you can know how the original function behaves on that exact point. And okay, and then the last part is the relationship between the general derivative and the derivative on exact point. Okay, so if you have the general derivative as we saw on here, it is a function just like the original function. So what is the relationship between the general derivative that is going to be a function like this and the derivative at a point? It means that you have a function and you want to know the derivative at an exact point. So you just have to replace what's the value of x on that point, like we did here. You just plug the x value on the function, and then you have the value of the derivative. Obviously, you can do it like this, using the formula of the derivative explicitly, or you can do it like using the principal formula. How? You just do the same process, but where you see an x, you put the value of the exact point you want to analyze, and then you can get the same answer. And that's it.